We're going to look at a systematic method of making reproducible measurements. And the first thing we need to recognize is that measurements are not exact. There's always a small amount of error associated with them, but they should be fairly similar measurements if we're using the same equipment and the same sample. So the way that we get similarity or precision in our measurements is to follow a very precise technique. And so this technique is called the 10% rule. And in general, what this means is we're going to record some number, and then we're going to record the number of marks past that number to the first decimal point. Now, at first, that's going to give you a number that's nonsensical until you realize that each one of the marks has a different value depending on what kind of device we're working with. So before we add our marks in, we're going to multiply them by the value of the mark. Now, the value of the mark differs from one substance to the next, but the way that we can always come up with the value is to find a range of printed numbers. So a high number minus a low number, and we're going to count the spaces between those printed numbers. Notice I didn't say lines, I said count the spaces between. So let's look at what I mean by that. In our first measuring device, this is sort of what a 10 mil graduate would look like. We have a number, a series of numbers, and what we want to do is find two adjacent numbers. Doesn't matter which two. I could choose the numbers 2 and 1, or I could choose the numbers 3 and 2. It doesn't really matter. In either case, if I choose between 3 and 2, again the high minus the low number, and I'm going to divide it by the spaces between 1, 2, 3, 4, 5 spaces between. Again, I didn't count lines, I counted spaces. Then what I find is that the value of each mark is 1/5, or in the decimal form. Now we can check and see if we're right by trying it out. If I were starting at the number 1 and I counted each mark, this would be 1.2, 1.4, 1.6, 1.8, and 2. So we did our calculation correctly. Now the value of the mark is going to change from one device to the next. So I'm going to make a note of what the value is for this one, and let's look at the next one. Again, I'm going to find two adjacent printed numbers. It doesn't matter which two. Now I drew this in to make it look like the bottom of a graduated cylinder because this would be roughly the 0 point. They just don't usually label 0 on graduated cylinders. So if I chose this bottom range of numbers, I would have 10 minus 0, my high minus my low, and between them I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. Each mark is worth 1. And if I wanted to check it, I could try it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's look at the third device. Again, if this is the bottom, they don't usually label the 0. Then my range of numbers could this time be between 5 and 0. And between the numbers 5 and 0, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5/10 or 0.5. Now the next device is a little bit different than the others because the 0's at the top. That's correctly how it's marked because of how it's used. You still follow the same process. You take a range of numbers, high minus low. So I could choose between 0 and 10, high minus low, 10 minus 0, divided by 10. Again, gives me 10 over 10. Each mark is worth 1. Now they're not always going to be pretty numbers, so you have to stop and check every time you work with the device. The next one, again, it doesn't matter what range. I could choose 3 and 4. Between 4 and 3, again, high minus low, there are 1, 2, 3, 4, 5 spaces. 1/5 is the equivalent of 0.2. And the last one, choosing a range of two numbers, between 40 and 20, for instance, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. So 20 over 10 gives me a marked value of 2. So now we're ready to make some measurement. When we fill a measuring device with a liquid, what we typically see is a curved surface at the top of the liquid. This is called a meniscus, and if we read this meniscus, the correct approach is to find the lowest point on that meniscus. And so in my measuring devices, this line that I've shown here in this dark red represents the lowest level of the meniscus that I'm reading. So I'm reading here. So let's make some measurements. We said that we're going to record some number and then how many marks to 1 decimal point past that number. So let's see what I mean by that. If I look at the first measuring device, my measuring mark, which is up here, is above the number 3 and not yet 4. So it's going to be some value above the number 3. Now we're going to count the marks that we've gone above the number 3. We've gone 1, 2, 3 marks, but I have to read 1 decimal place in there. Exactly halfway between the marks would be 0.5. And it looks like my line is just about half the way between. We may disagree on that, but that's okay. But what I see is I see the number 3, and I see 3.5 marks. Now we're not quite done because we said we had to multiply the marks by their value. And their value is here. So for that measuring device, 0.2. So if I do this math, I come out with the number 3.70. So let's look at the next one. Again, I'm reading this dark red line up here. It's above the number 10, and it's 1, 2, 3, 4, 5, 6 point something marks. I think this one may be slightly above halfway, maybe 6.6 marks. Again, we might not both agree on it, but we'll be pretty close. Now, again, I can't do this addition until I take into account the value. Our value for that device is 1. So when I do this math, 10 plus 6.6 times 1, I get 16.6 as my measurement. Let's look at the third one. Our measurement is above the number 5. It's 1, 2, 3, 4, 5, 6. This time it looks to me just slightly less than halfway, so I think maybe 6.4 might be a good number of marks. You may disagree, maybe you think it's 6.5, but we're going to be really close. On that measuring device, the marks are worth 0.5. So if I do this math, this is going to give us a value of 8.2. In this next device, notice that it's marked increasing as you move down the device. Now, we don't take a ruler and measure from 12 backwards. We always measure from low to high. So this device has measured past the number 10, and we've got maybe 1.6 marks before I wrote over it. Maybe it's 1.5. Again, we don't have to agree on that. And on that device, my marks are worth 1. So on that device, I'm getting 11.6 as my reading. Again, the 0 is up here. So we have gone past the number 1, and we have gone 1, maybe 0.8 past the number 1. So 1 mark, and again, we're estimating to the decimal point there. And on that device, the marks are worth 0.2. My measurement would be 1.36 if I did the math. The last one. This time the numbers are going up. They don't write the 0, but we know that it's there because from here to here is 20. The same distance on this device must be subtracting 20. So again, we're going to record what we see. We've gone above the number 0. We've gone 1, 2, 3, 4, 5, 6, 7, 8. I see it as maybe 8.4. and this time the marks are worth 2. So on that device, if I do that math correctly, I come up with 16.8. So this is called the 10% rule because 1/10, which is the decimal point we're working with, if we're working with decimal points, we're counting by tenths, 1/10 is the same thing as 10%. And so that's how we measure reproducibly using a piece of equipment. Now we're almost done. The last part of making our measurement is to acknowledge to our readers that we may have made an error. The errors are also established for that device. According to the 10% rule, our error or our uncertainty, sometimes it's called the tolerance, sometimes it's called the precision. All of these words are trying to tell us that there is always some little amount of variation in any measurement that we make. And the amount of precision depends on the individual device. Specifically, it depends on the markings on the device. So once we calculate the value of our mark, we also could calculate the value of our precision. The value of our precision is always whatever your marked value is divided by 10. So if we look back at these devices, we know how good they are. The uncertainty on this is going to be 0.2 over 10 or 0.0. The uncertainty on this device is going to be 1 over 10, where again I'm taking the marked value, dividing it by 10, which means my uncertainty is 0.1. 0.5 over 10 gives us an uncertainty of 0.05. 1 over 10, again, whatever your marked value is, divide it by 10, means that this one is good to the 0.1. 0.2 divided by 10 gives us an uncertainty of 0.02. 2 over 10 gives us an uncertainty of 0.2. So when we record our measurement, we record not only the measurement that we get using the 10% rule, but we're also going to say how much error is expected with each of those measures, because we're saying that we could have been off by this amount. So in the first measuring device, 0.02. In the second measuring device, 0.1. Now it's not a coincidence that there are 2 decimal places here and our measurement has 2 decimal places. 1 decimal place, 1 decimal place. It's not a coincidence how the precision is calculated. It's always 1/10 of the mark, which means we get 1 more decimal place than the mark had. So if you didn't record a 0 here, good, you shouldn't have. You're only allowed 1 decimal place in this value, but this one requires 2 decimal places because this device is able to read 2 decimal places. Then our recorded measurement also has to show 2 decimal places. 1 decimal place, 1 decimal place. 2 decimal place, 2 decimal place. 1 decimal place, 1 decimal place. And now we've made measurements that are reliable and reproducible.